Okay, hello everyone. I think this will be, the last part for this um, sort of uh, part of the eigenvalues in the system of linear differential equations. We have the distinct eigenvalues, the repeated eigenvalues, and the complex eigenvalue, which I think we haven't yet finished this part. So if we could write the this B1 and B2, we could write this B1 and B2 as let me write this. We can write the B1, and we could simply say that this is part of the real number, and then we input the eigenvectors, and B2 is the part of the imaginary, and K1. This is just as symbols, which means that this part of the B1 is going to be the real number, and part of the B2 will be the imaginary number. So this will be the real, and this is imaginary of the eigenvectors K1. And then back to the these equations, then we can write that the K1 is, this is just to finish off the equations. So this is 1 and 1 minus 2i, which means that we have the real part is 1, 1, and the imaginary part will be 0 and negative 2. Okay, so this is the real and imaginary. Okay. So we can say that from here that B1 is 1, 1, and B2 is 0, negative 2. This is just to separate between the real parts of the eigenvectors and the imaginary parts. And have we discussed when we will have a midterm? Not yet, right? So I think since I need one more part about these eigenvalues, which are related to what we call in matrix as diagonalization, which I haven't yet introduced. So I will have some small introduction of that part and adding that as a solution in linear differential equations. So I need at least, because this week holiday, right? So I need to count how many days we are still going on. So we still have on 8, and then I think I need 12, and 15 is over, we can review. So I believe we need to delay until 19. Is it okay? Okay, right? And you are having another schedule as well, right? I mean, in the previous weeks. So I think 19 should be okay, right? For the midterm. Okay, right? 19 April? Okay. 19 of April, right?
It's Friday or Monday?
Friday. Because I need to take 2 hours.
Fair enough.
Yeah. 1 hour is only for quiz. For exam, for midterm and final, I need at least 2 hours. Okay. So let me just write here our midterm will be Friday 19. Okay. Okay, so now let me just give you some another examples on this complex eigenvalue, and if we finish the eigenvalue, then let me go through the introduction of diagonalizations. And Okay, let's start the one example on the complex eigenvalues. So suppose that we have this system, okay, and we have the boundary value, okay, the boundary value. So since this is two by two matrix, which is, I believe, should be okay with you, right? I mean, if 3 by 3, you need more time to calculate. So if 2 by 2, it will be okay, and I think mostly in the exam I will use 2 by 2, okay? Just to have you focus more on the details, not in the calculations process. The calculations, I hope you are familiar with your calculators, and if you have, I think some calculators can be put into matrix mode, which can be helpful. But if not, I hope you can find, if you haven't, you can find your way to use that. Okay, it will be pretty helpful. But anyway, so to solve this, first is finding. So first procedure is eigenvalues, right? So let me write here, eigenvalues. So we take the determinant for A minus lambda identity, which is going to be the diagonal matrix. So 2 minus lambda, 8, -1, -2, negative lambda. Which we have here is 2 negative lambda and minus 8, right? And after some calculations, you'll see that we can cancel in the lambda, 2 lambda with -2 lambda, right? So we have lambda squared minus 4 plus 8, so plus 4, right? And this is going to be equal to 0. So we get that this will be a complex, which we can see that this is having -4, right? So the lambda, or we could say lambda 1 will be 2i, and lambda 1 and then bar, this means this is the conjugate for the complex, okay? So sometimes we write lambda 1, lambda 2, but for complex, for most of the case, we are going to write as the same but with the bar on the top. This is symbolized that this is going to be the conjugate of the eigenvalue, the lambda 1. This will be -2. And then each for eigenvalue we are going to evaluate to find the eigenvectors. So let me write eigenvectors. So first is 2 minus 2i. I think we can just write the system equation directly. No need for row operations, right? For 2 by 2. Plus 8k2 is 0, negative k1, and then plus -2, -2i k2. All right, now we have k1 is, we can focus on the second equations that we can follow. Negative so we can take this as -2 plus 2i k2, right? Just playing with the negatives. And then if we let the k2 equal -1, then we have k1 is -1, and then this will be 2 plus 2i. Or we can separate this, becomes the real part and the imaginary part. Okay, perhaps I haven't discussed you about the how to stack the eigenvalues and eigenvectors. My suggestions, okay, to help you to write in a clear and concise way is first, for every part of the eigenvalues, for example, here's the complex. We write the first one is 2i, the second one is the counterpart, the conjugate. For the distinct eigenvalues, for example, if you have something like this, okay, this is I'm just writing some numbers randomly, okay, maybe we have 3, okay, so you have 1, 5, and -2. Start numbering from the lowest one, okay, which means the negative one. So the lambda 1 will be negative, lambda 2 is 1, lambda 3 is 5. This is to help you to rearrange more clear and concise, and make sure that all the numbers are confirmed at the end. And by doing this, which means that if there are eigenvectors, then you will have eigenvectors 1 here, k2, and eigenvectors 3. Okay, this is just my suggestions to help in the computation and to avoid some repeated mistakes that might happen. Okay, anyway, so we have, this is the B1, and this is the B2. So the real and the imaginary, right? And then remember that the complex, it should be so eigenvalues for complex should be in terms of alpha and beta, right? Alpha is just a real number, and beta will be the number in which they are the imaginary. And now we have our eigenvalues is, we don't have any alpha, right? Alpha is 0. So we can write here that alpha is 0. And our beta, we can have 2, or let me just write here, it's 2 and -2, okay? So we could write the whole equations, the system, C1, basically we write based on what we have done here. Let me just go back just for a while. So we are going to write based on this, okay? So this will be cosine, sine, cosine, sine for every one x. So we have written down, and this will be 2, -1. So this is alpha, and then cosine 2t, and minus, this is 2, 0, sine 2t. This is the first part, and then plus constant 2. We write now the beta, or the B2, sorry, the B2, 2, 0. This will be cosine 2t. So as long as you write the first part correctly, the second one should be the reverse part. Okay, so you are going to reverse the B1 and B2. This will be sine 2t. Where is the alpha? The alpha is supposed to be having the exponent with power of alpha, but alpha is 0, so it will be 1. So it should be here, okay? Should be around so at the end of every part, there will be exponent. Supposed to be this exponent here. So exponent alpha t, this is also exponent alpha t, but alpha is 0, okay? So we can just write 1. Or you could write combine all together for both of this component. So 2 cosine 2 theta or t minus 2 sine 2t, and this will be minus cosine 2t plus c2 and this will be minus sine 2t. Oh, and that's it. But we are not done yet, because we have the boundary value, which is the, let me write here that the x at 0 to -1. Let me erase this one first, because if I write here and I put the notes, you'll confuse why I wrote down this part. So let me put here the boundary value. Let me put here, which I will take the at 0. So we have x will be c1, that will be 2 minus 0, so 2 minus 1 plus c2, this will be 2, 0, and then 0. Okay, and this will be, or let me just write here at the x0, this will be 2, -1, and we can get every, so 2c1 plus 2c2 equal 2, negative c1 equal -1, so c1 is 1. And c2 is 0. And you can just put everything back, which means the second part will be gone. So this will be equal to, let me make a little bit smaller. So this will be x, 2 cosine 2t minus 2 sine 2t. This is negative cosine 2t. Okay, that's the solutions. So let me write here just to let you know which steps these are. This is going to be the complex general solution. So complex general solution is based on the alpha and beta from the complex eigenvalue. And all the coefficient is based on the eigenvectors. And then this is the last part. Check the boundary value. Okay. Okay, so I will move away for a little bit just to get some small introductory of the diagonalizations in matrix. So let's move to just a next page for a small amount of time. Hopefully, maybe if not today finish, maybe by next week we can finish off this. So what is diagonalizations? So suppose that we have the n by n matrix of A. Then we are curious if we could find another matrix, non-singular matrix, we call the matrix P, such that if we multiply P inverse, multiply with A, and then multiply with P, this will equal D, which is the diagonal matrix. Okay, now to begin this diagonalizations, let's start with this AB. Okay, AB multiplications. So AB are from two matrices, matrix A and matrix B, and of course, if we multiply these two, this will be the result. Okay. Now, if right here, so if column matrix B, rewrite, so we write as vectors x1 and x2 okay. Then we can express the matrix AB, or let me write with the black. AX1 and AX2, which means that this will be the column 1 and this will be the column 2. Okay. And in general, we can express the AB as A, X, X1, X2, X3, 4, and until Xn as AX1, AX2, until the AXN. Okay. Depends on how many n by n. Where the x1, x2, until the xn, all of them are columns of matrix B. Okay. Now, before we move on, we need to find what is the matrix that can be diagonalizable. Okay. So this is diagonalizable matrix. So let me. This is D. Okay. So let me write some notes here. So if we can find n by n non-singular matrix P can be found so that the P inverse A, P equal D, and this is equal to is diagonal matrix. Suppose that we can find this P. Then we say the n by n matrix A, or let me write here, then that the matrix, the n by n matrix, or just matrix A, can be diagonalized. And P diagonalizes A. And we put over there, and then we put this a little bit to the left, and getting smaller a little bit. Okay, first assume for our arguments, so assume A is 3 by 3, diagonalizable matrix. Okay, so we need to find P such P inverse AP equal D. And if we multiply on the left side with P, with another P, then we need to find where the AP is equal PD. Okay, and D will be written as this clear and nice diagonal matrix, which only has the diagonal in terms of value. Okay, later you will see that our eigenvalues will result in the eigenvectors. And the eigenvectors, basically, if we are going to multiply with A, is basically the same thing as our P that we can try to check or to confirm, right? Let me write a little bit on the right side here. Okay. So first, we can write that if we can say that we have P1, P2, P3, this is columns of matrix P, then right here, the AP equal PD, we can rewrite this as AP1, AP2, and AP3. Just the same as we did on the first notes here. Very similar. So that is how we can write that. And the right side of equations will be the diagonal I will write the D first, but it's supposed to be similar. D2 to P2 and D3 P3. Okay. So we could see that we have the AP1 is that, and all with each diagonal and P. If you remember what we did in the eigenvalues, how we find the eigenvalues, the D11, D22, D33 are eigenvalues, right, of A with eigenvectors P1, P2, and P3. Since we assume P is non-singular, then all these eigenvectors, it need to be linear independent. Because our assumption is P is non-singular. So if A diagonalizable, then the columns of P consist of linearly independent eigenvectors of A. Now this will be our clue. Okay, so basically what this is about is actually the matrix P will be our eigenvectors. Okay, so we find the eigenvalues, we find the eigenvectors, and if we want to write and finding the diagonal matrix, then we are going to arrange this P so that the P will consist of all the eigenvectors that we have found. Okay. Then of course we need to make sure that this is going to be linear independent. But since this is our assumptions that we make that the P is supposed to be non-singular, this should be linear independent. Okay. At the later theorem, we're going to see whether we can find or we can determine whether a matrix can be diagonalized or not. So we need to have a condition, okay? How the matrix can be diagonalizable. For sure, the first theorem should be linear independent. The eigenvector should be linear independent. And then we need to know how many the eigenvectors will be. It's also need to be we need to also calculate how many. Okay, so basically first, this is the first theorem that I think we have shown from the previous part. But let me just give you a quick proving by taking each one of the multiplication of A and K, which we have the A K1. The previous part is from the AP, but we know that P is eigenvector, so we could start from AK. So AK1 means that this is going to be lambda 1 K1, and AK2 will be lambda 2 K2. And so if we have these three forms, so we have the P will be K1, K2, K3. Now this is why I'm suggesting to rearrange the eigenvalues based on the value. Okay, you can start from maybe the lowest one, and then starting to increase as we follow the row. Okay, and assume that P is non-singular. Now we can write the AP as AK1, AK2, AK3, or this is each one of them multiplied with its eigenvalues. Okay. Or we can write this as can split, and this becomes the diagonal. And if we multiply with the P inverse, let me write here, just giving you the note that this is going to be the P inverse, or let me write with a different color, the P inverse, and then multiply the left part also with the P inverse, then we get the D. Okay? So the idea, we find the eigenvalue, we find the eigenvectors, we arrange the eigenvectors to be the P, to be our P, this P, okay? And then we find the P inverse, then we multiply P inverse and P. So we multiply the P inverse to get our diagonal. So P inverse multiply with A, multiply with P. That will be the diagonal, our diagonal matrix. And also, if you remember when we learned the eigenvalue, so if we have the n by n matrix, okay, it will have the n linearly independent eigenvectors. Whenever it has the distinct eigenvalues. Okay. So again, I will add here the n by n matrix. Has n linearly independent eigenvectors whenever it possesses n distinct eigenvalues. Okay, so then it will connect to the next part of the theorem, which basically says that we have n by n matrix. It has the n distinct eigenvalues. It should be diagonalizable. Okay? So this will be your clue. So you see the matrix first. If you see 2 by 2, it has 2 eigenvalues, distinct eigenvalues. You can directly say, oh, it's diagonalizable. So you could find the eigenvectors, you can rearrange the P, find the P inverse, and you can multiply P inverse, multiply with A, multiply with P, and you got your P, your diagonal matrix. Okay. It has some steps, but clearly it has all connected, eigenvalues, eigenvectors, the diagonalizability. Also later, we're going to see that these diagonalizations will also can be solved, or it can solve our linear differential equations. But that will be, I think, next part. Okay, any questions so far? I think this diagonalizations, maybe I'm not sure whether in linear algebra we'll also get into this diagonalizations, but I think it has some connections. Okay, if there's no questions, I need to have some feedback questions. because we haven't done for sometimes. Okay, wait for a while. Okay. Okay, that's the QR code.